Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on OCR salters kinetics. Now this falls into the CI topic, or the chemical industries topic, and so everything in this video is actually dedicated to the OCRB salters specification. So it's not like other resources where you might use where they might be quite generic, or you might wonder if they're actually related to your specification. All of these videos that I do, so the other ones with the black screen, are dedicated to salters. So if you're studying that, then it is absolutely perfect for you. There's actually a full range, like I say, it's not just this one. There's a full range of revision videos on Allery Chemistry YouTube channel. So the revision videos are the black videos, the ones with the black backgrounds, and I've also got some whiteboard tutorials as well that go through generic information. So for example, I talk about bonding and titrations, etc. So it targets particular topics, but there's loads of information on Allery Chemistry YouTube channel, and they're all for free. So all I ask is you hit the subscribe button. That'll be absolutely fantastic. It keeps the channel alive, and as long as people keep subscribing and watching, then I'll keep making them. Also, these videos here, they are they're revision slides that I've made. So you can purchase them from the link in the test shop. If you want your own copy of them, you can purchase them in the link below, and they're really good value for money. You can use them on your smartphone, on your tablet, on the move, or I know some people who print these off and annotate them and use them as revision notes as well, but they're all available. If you just click on there, the full range for year 1 and year 2 is available there. Okay, so like I say, this is actually dedicated to the OCRB salters course, okay, and so meets the specification points that you can see on there. So in this video, we are going to be looking at things like rate equation. We're going to be looking at rate expressions and a few calculations in relation to that as well. We're going to be looking at half-lives as well, and the reactions involved there in terms of orders. We're also going to look at the Arrhenius equation, which is a nice equation towards the end there, and then right towards the end of the video, then going to look at rate determining step. So looking at rate determining step and multi-step reactions. So we're going to be looking at a little bit more information with regards to that as well. So that's the running order for this video. Okay, so let's start with rate of reaction first. Because this topic is on kinetics, it's very important that we obviously introduce this properly and we look at what that means. So kinetics is to do with how fast something works, so how fast a reaction actually goes. So we're going to be looking at rate of reaction for this reason. So we need to know the definition of rate of reaction. So rate of reaction is the change of concentration or amount of reactant or product that's produced or used up per unit time. Okay, so that definition is vital. You've got to remember your definitions because it's easy marks really, but you've just got to try and remember them. So look at this equation. The equation is really important as well because this actually measures the rate of reaction. And so if we had to put that definition to equation form, we would get amount of reactant used divided by product made, or product made divided by time. Okay, so we're depending on what we're measuring, so that's going to have a bit of an impact, obviously, on what we're going to be looking at. The question will specify, obviously, if we're talking about reactants being used up or products being formed, it will specify in the exam. Okay, so how can we actually measure the how can rate be measured in experiments is very important, because we can't look at a reaction and guess its rate. We've actually got to do it practically. So the practical side is really, really important. So we can look for, depending on the type of reaction, it will depend on what experiment we're going to do to measure the rate. Now, if our reaction produces a precipitate, then we can use this method where we're going to work out how long it takes for that precipitate to form. So an example would be, and you might have seen this using sodium thiosulfate, for example, where you have a disappearing cross. You have a bit of paper, you draw down your cross underneath that, so you can see there. So there's your cross, so we put the cross underneath there, the beaker goes on top, we add our chemical, this goes cloudy, and we look down the top of the conical flask, and we're trying to see when it goes cloudy. Now, the problem is with this experiment is that actually it's really difficult to know exactly when it does go cloudy. And that sounds a bit strange, but this reaction may change slowly. It may form the precipitate slowly. So at which point do you actually stop the stopwatch and measure the rate of reaction? So with these types of reactions, it's really important that if you are going to use this method, that you use the same person to measure it, because one person's, well, you've got different perspectives, should I say. So one person may look at the reaction and decide that it hasn't quite changed. Somebody else might look at it and say it has changed. So, at a specific time. So make sure you're using the same observer for this. So another example is mass lost. Okay, now this one you might have seen. We use a top pan balance for this one, and we put a conical flask on top of the top pan balance with our reaction that's occurring in the conical flask. Now what happens with this one in particular is that a gas is produced, and the gas is allowed to escape from the conical flask, and so that means that the mass in the container is dropping because we're losing some of our product. And so therefore what we can do is measure how much mass is lost per unit time. So over a particular time frame, so that might be every minute, every 2 minutes, every 3 minutes, depending on what your frequency, the frequency is that you're measuring against. So it's a fairly accurate method. However, we've got to use a fume cupboard, because if the gas that's produced is toxic, we've got to use a fume cupboard for that. If it's not, then obviously that's fine. So it depends on the type of reaction that we're doing. Another one is similar to this, is the volume of gas that's produced. So with this one, instead, we use a gas syringe. So here we're going to measure the amount of gas that's being produced. So we basically allow the reaction to proceed, to carry on, and then the gas that's produced enters the syringe, and we just measure in the volume of gas that's produced per unit time. So that's per minute, per 2 minutes, whatever frequency you're going to use. What I must state here actually is, I've done this myself, where the reaction conditions are maybe quite vigorous, and they produce a large amount of gas. So what happens is the gas then enters the syringe, and it literally, the plunger effectively flies off the other end because you've produced too much gas. So obviously you've got to make sure that the syringe is the correct size for the reaction that you're doing. That's one of the downsides, I suppose, with that. So carrying on with how they can be measured, we can also look at a change in pH of a reaction as well. So as a reaction proceeds, the pH may change, and so that might be the case if H+ ions are being produced as a product, or if H+ ions are being used up as a reactant, and we can measure the pH change. And we do that quite simply by measuring using a pH meter, and we measure the change in pH over time, and then we plot that graph of the change of pH against time, and we can monitor the rate of reaction there as well. And another one is titrations. Yes, you wouldn't be chemistry without titrations, would it? So another one is using titrations to do this. And actually what we can do is monitor the concentration of a reactant or product by taking small samples, or we call them aliquots, at regular time intervals and then titrating them. So for example, if we have our beaker with our reaction, we set the reaction away, and then what we're going to do exactly at, say, 30 seconds, we're going to take a sample out and we're going to quench the reaction. Now we can quench that by using a reagent, for example, or we can cool it down, or there's numerous ways in which we can effectively freeze that reaction in time at 30 seconds. And then once we've done that, we can then titrate it against a known substance, and we can work out the concentration at that point. And then we can take regular intervals and measure the concentration over time, and then we can work out rate of reaction from then. So like I say, when we take that aliquot, we must slow that reaction down immediately. If we didn't, the reaction would just continue within the pipette that you've used to draw your liquid up with, let's say, 30 seconds. So if we didn't, like I say, the reaction would just continue. And obviously the product and reactants would change in that time. So the number of ways in which you can slow down the reaction is by, like say, diluting it with deionized water. It could be cooling it down if it's a reaction that stops when it's cold, or like say, add a chemical to it, a quenching agent, to effectively halt the reaction at that point at 30 seconds, and we get like a snapshot of the reaction at that point. Okay, so if a reaction has a colour change, then what we can use a colorimeter to actually measure the rate of reaction. Now you might have a colorimeter, if you've got a school or college, you might have some colorimeters around, They're fairly straightforward instruments to use. Basically, a colorimeter is just measuring the absorbance of light by the colored sample. Okay, so the more concentrated the sample is, obviously the darker it's going to be if it's a colored substance, and that means that less light can actually get through that darker substance, and so therefore more light is absorbed. Now, a colorimeter, as you can see in the diagram there, the picture, sorry. So there's the picture. You can see we have our sample there, and we're just measuring the absorbance. Obviously, light is shone through this dimple here, and it's measuring the absorbance of light through, and it'll display it on the screen there on the side. So a classic example of this would be using the reaction between propanone and iodine. Now, this reaction goes from a brown colour, which is iodine solution, to a colourless solution, because you form your iodine-based compound here, your iodines and H+. So all of these products are actually colourless at this point. So we're going from brown to colourless, so we can actually monitor the reaction basically as it goes. So this is going to get paler as the reaction proceeds. Now, the quicker that gets paler, the faster the rate of reaction. So to do this, what we need to do is we have to actually plot a calibration curve, and this is created by making up a range of known different solutions of the sample that we're testing, and then we measure the absorbance of each one of them and plot them on a graph like this. So you can see here that we've actually done various different ones. So we've done 1, 2, 3, 4, 5. We've done 5 set samples here. And what we've done is we've made the concentration, we've fixed the concentration. So we've done a concentration here, a concentration here, a concentration here. So we made them up to specific concentrations. We've measured the absorbance of each of these, as you can see, and then we've drawn a line here. And then this is our calibration line that we're going to be using. So an experiment like the one above is set away. Samples are taken regularly from this reaction. So we basically set the reaction away. We take samples from it, put it into here, as you can see, and then we measure the absorbance of this reaction at this moment in time. So this might be a sample from a bigger container which contains the main reaction. And then what we do is we then use that calibration curve to find out the absorbance using the absorbance to find out the concentration of our substance at that time, and then we can plot that against time on a graph. So it's concentration against time, so concentration against time. So you can see here that if we had, let's say, our chemical gave us an absorbance of 0.8 at a particular time point, then what we can do is we use our calibration curve, we go across here and then down here. Okay, and that will then tell us the concentration of our substance at that time. So fairly straightforward. So you can see there's various different ways in which we can measure rate of reaction using experiments, but it really does depend on the type of reaction that you're actually doing. So if it's producing a gas, for example, if it's producing a solid, is it changing colour or pH, etc. So you have to fit the right practical method to the right reaction that you're doing. Okay, so what we're going to do is then going to use this to calculate the rate from a graph. Okay, so rate can be found from the gradient of a tangent on a curved line of best fit. Okay, so obviously all the results that we've taken from there, we need to plot it onto a graph, and these are the graphs that we're going to plot after taking the results from our practicals. So an example would be this. Now you can see here that we've got our concentration of our reactant on the left there it is, and our time on the right. So here we're looking at the concentration of reactant is obviously what we're reacting together, and we're monitoring how that concentration changes over time. So you can see here that this one, we start with loads of reactant and it's decreasing over this time period. But to find the rate of reaction, what we need to do is draw a tangent, which is a diagonal line at a specific point on this curve. And then what we need to do is extend that line right across that graph, because the bigger the better. It means you can read the graph a lot easier if you draw a large gradient or large line. And the gradient is working out the rate at a specific point on this curve. Okay, so you might have seen in college or school where actually your teacher may be telling you to draw your graph bigger than half the page. I certainly did. Your graph must be at least half the size of your graph paper. If it isn't, it's going to be too small. So ideally it needs to be a decent size so we can actually use the graph. There's no point in plotting a graph if you're not going to use it later on. So this is what we're going to be doing. So here we're going to work out the rate of reaction at 3 minutes for this particular reaction. So what we do is you draw a tangent that hits right at the 3 minute point, as you can see there. So there's the 3 minute point there. Okay, and it's going to go up here, and that tangent is hitting right against the curve at that point there. Then to calculate the rate of reaction, we need to work out the gradient of that. So the gradient is the change in y over the change in x. Okay, so y is this axis here, and x is this axis down here. So we're going to put the numbers in. So oops, I think something has, oh no, there we are. Okay, so we've got our table, we've got our lines here. So this is showing the difference between here and here. So we're working out our gradient at this point. So then what we're going to do is put our numbers in. So we've got a difference of 0.3 on the y-axis and a difference of 4 on the x-axis. And so then what we're going to do is put the numbers in to work out the gradient. And so you can see the gradient is 0.075 moles per dm cubed per minute. Now, the reason why it's per minute is because if you look at the units, you might think, well, how do we know they're the units? When we're working out the units, we do this, which is the y, divided by that. So it's that per whatever it is. So make sure you look at the units really carefully on your graph to make sure that you're given the correct units for your rate of reaction. So you can see that it's fairly straightforward. We've just got to work out the gradient, obviously draw a tangent there, and then work out our gradient after that. Okay, so this is how you'd work out the rate from a graph. This is a curved graph here. Some of them will be curved. You can also get straight line ones, which are much more straightforward than your curved ones, because you literally just find the gradient of a straight line. You don't need to put in a tangent. So the tangent is only put in when we actually have a curved graph. Okay, so what we're going to do is we're going to look at another type of experiment where we're looking at rate of reaction, and these type of experiments are quite unusual, well, not unusual, but they're quite clever experiments, because actually they kind of change colour of their own accord, and we call these clock experiments. So a clock reaction is where you can time how long it takes for a reaction to actually occur. And the clock reaction, as we'll see later, we'll look at this a little bit later, is used actually to simplify the initial rate method. Okay, so we're going to look at initial rates later. But most reactions, like iodine clock is an example of a clock reaction, can be monitored by sitting the reaction vessel on some paper with a cross on it. So we've seen this type of reaction. You might have seen this type of reaction before already. Okay, so we time basically how long it takes until we can't see the cross through the beaker. And there is a colour change, for example, so you might get a colour change or precipitate that may form as well. And so this is known as the end point. So it's the point at which we can no longer see the cross through the beaker because the solution has changed colour, so you can't see it. And so calorimetry can also be used as well as colorimetry. Can also be used as we've seen just before. Okay, so essentially, the quicker the clock reaction, the faster the initial rate of reaction is. Okay, so that kind of makes sense. So when we set this reaction away, if that colour change happens much quicker, or we can't see that cross, until in a really quick time, then effectively the rate of reaction is going to be quicker. And so we make 3 assumptions here for these types of reactions, because we're measuring initial rate, which as it suggests is the rate right at the start of the reaction. That will come a lot clearer later on when we look at calculations looking at initial rate. So the 3 assumptions you make is the temperature of the reaction remains constant, so it remains the same. Okay, the concentration of reactants doesn't change significantly during the time period of the reaction. Okay, and the final assumption is that the reaction has not proceeded too far when the end point is seen. So in plain English, effectively what we're saying is that the temperature must be the same. So we're assuming that the temperature isn't changing throughout this reaction. So the temperature is constant all the way through our equation, all the way through our reaction. The concentration of reactants doesn't change significantly. So in other words, the amount of reactants and products remains pretty much unchanged, so we can exclude that element out as well. And also the reaction has not proceeded too far when the end point is seen. In other words, we're not overshooting it. So for example, if the cross has, or the end point has arrived actually sooner than what we actually observe, so we assume that when we do observe that cross disappearing, that is the end point. Okay, so on the basis of these assumptions, what we can say is that the rate of reaction remains constant throughout, so during the time period we are measuring. So whatever that rate is, so we measure the time period. For example, we might alter the concentrations of various substances and measure the rate of reaction for each of these, and we can monitor that, but we can assume that the rate, the initial rate, is equal to the rate that we calculate by doing the full experiment, I can see on there. Okay. So you'll see this will come into play quite a lot when we look at the calculations to do with initial rate. But basically, as a result, the rate of the clock reaction is a good estimate of the initial rate of reaction. So clock experiments are really useful for initial rates, which you will see in use later on. Okay, so we're going to look at, Salters want you to know a little bit more information about a specific clock experiment. And this clock experiment is called an iodine clock experiment. And basically it has this reaction. So we have hydrogen peroxide in acidic solution reacting with iodide ions, and it forms water and iodine. Okay, so this is the overall clock reaction. You can see here this lot is colourless on this side and this is coloured on this side. So we're looking for this colour change. So you can see how it's quite a good experiment in terms of a clock reaction. So all we have to do to this reaction to get it going is we add sodium thiosulfate and starch. Now starch acts as an indicator because it reacts with iodine. It turns this dark black blue colour. Okay, and we add that to excess hydrogen peroxide, as you can see there. So the sodium thiosulfate reacts immediately with the iodine that's actually produced in this reaction here. So that's the sodium thiosulfate that we've added in there, and effectively the reaction then forms this. So we've got the sodium thiosulfate reacting with the iodine that was produced in this reaction here. That produces I- ions and then S4O6 2- ions there. Okay, so when there's no more sodium thiosulfate left, okay, so in other words we've used it up, then the iodine will then react with the starch, and this will give this deep blue black colour. Okay, and so what we can do with this experiment, the variations of this experiment, is that if we vary the concentration of iodine and or hydrogen peroxide and we keep everything else constant, this will result in the time taken for the blue black colour to appear change. Okay, so this will change depending on the concentrations of iodine and obviously peroxide as well. And so what we can then do is work out the order of reaction from that. Okay, and we'll look at orders later on in this video as well. But you can see here that by altering the concentrations of some of our reagents, we can then monitor what effect iodine has, or altering the concentration of iodine has on rate of reaction, and altering the concentration of hydrogen peroxide on rate of reaction as well. Okay, so it's just a specific example which you need to know, which is the iodine clock, as you can see on there. Okay, so now what we're going to do, so remember we talked about initial rates, and we looked at obviously what iodine clock reactions can be used to work out the initial rate of reaction. So now what we're going to look at is something called the initial rates method. Okay, so this is where we're going to use the results from our clock experiments, and we're going to use that to in this method called the initial rates method. So the initial rate is the rate, like I say, right at the start of the reaction, so it's immediately right at the start. So initial rate is basically worked out by seeing how long it takes for a specific amount of product to form at the beginning of a reaction. Okay, so for example, how long would it take to produce a specific volume of gas, or it might be how long would it take for a colour to appear, for example. So it's right at the start of the reaction. So what we do is we then, once we've done that, we need to repeat the experiment several times, but what we're doing is changing the concentration of one of these reactants. So a bit like what we were mentioning before with the iodine clock experiment, we could alter the concentration of iodine or hydrogen peroxide, and we can run it, say, at 0.2 moles per dm cubed of hydrogen peroxide, then we run the experiment again, measure the rate, then we run it again with 0.4 moles of hydrogen peroxide, measure the rate again, then we do it at 0.6, measure the rate, 0.8, measure the rate, etc. And we keep going, and we basically measure in the rate of reaction, looking at the impact that change in one of them substances has on the rate of reaction. So some of the assumptions that we make, remember, is that the temperature remains constant. So this is just a reminder, really. The temperature remains constant. Ensure that the concentrations of any other reactants don't change significantly. Okay, and then we use a large amount of this. So we use it in excess, and we ensure that reaction has not proceeded too far when we take the measurement. You must make sure you understand these assumptions when we are collecting data for initial rate, for example. So these are the assumptions that we're making. So the rate of reaction will be constant during the time period when you're taking measurements if the assumptions are adhered to. Okay, so we try and keep all of these the same. Okay, we try and keep them all the same as much as we possibly can. Okay, so the rate of reaction will be a good estimate of the initial rate, as I said before. Okay, so using that, we can then use that initial rate method to work out orders. Okay, so the rate equation links the rate with concentrations of substances. Okay, so we looked at how we calculate the initial rate. This is where we're going to use these initial rate figures to work out the rate constant. Or the rate equation. So the rate equation is given as this. So rate equals K, and that's capital A there, which is our substance A, to the power of little a, and then B to the power of little b. So you can see here that rate is moles per decimeters cubed per second, as an example. Your rate constant is K, so the units vary for this. You'll have to work that out separately. And your reagents here, so this is the concentration of the substance. So for example, if in this example our general equation is A plus B gives C plus D, then we can see that B is one of the reagents in this reaction here. And the little letters here are orders of reaction. Okay, so an order of reaction is something where it's a power to which a concentration is raised to in the rate equation. So basically, it tells us how the concentration of the substance affects rate. So in other words, if we change the concentration of A, let's say if we double A, does that also double the rate? Are we going to get our reaction going faster? Or does it quadruple the rate? Or does it have no effect on rate? This is really important for chemists, because if they know what impact a chemical have, changing the concentration of chemical can have on the rate equation, then they will obviously devise a chemical reaction where they're trying to optimize the rate. If it has no impact on rate, then the chemist will not change A or B, or they'll not change the reagent they'll not change the reagent to improve the rate of reaction. So some reagents do impact rate, some don't. Okay, and the orders basically tell us how much it impacts the rate. So for example, we have 3 different types of order that you need to know, and the first one is zero order. So zero order is where changes in concentration has no effect on rate at all. So for example, if we double the concentration of A, rate doesn't do anything. Okay, so if you're a chemist trying to improve rate, you wouldn't change the concentration of this substance because it won't do anything anyway. First order is the next one. So this is where changes in concentration is actually proportional to rate, or the change in rate. So for example, if we double A, then rate will double. If we quadruple A, then rate will quadruple. Okay, so it has the exact effect, so it's directly proportional to it. And the last one is second order. Now, second order reactions are squared proportional. So what that means is, let's say, for example, if we double A, then the rate of equation will, the rate of reaction will quadruple. So it has a disproportionate effect on that. So that could be quite good, because actually we only need to make a small change in the concentration of a substance, and we get a much bigger change in rate relative to it. Okay, so orders can only be determined by experiment. We can't work them out just by looking at an equation. We must actually do the experiment and work out the orders from that. Okay, so let's have a look. So the rate equation links rate with concentrations of substances, as we've seen there. Okay, now the rate constant, which was K, this is a number that allows us to equate the equation. So it means that we have rate equals K and the concentration of our substances. So K is just there to kind of make up the difference between rate and the concentration of our substances. So the rate constant is only fixed at a particular temperature. Okay, so if the temperature changes, then so does the value of K. So, for example, K increases when the temperature increases. Okay, so the value of the larger the value of K, the faster the rate of reaction. Okay, so if we've got a large value there, large rate constant, then our reaction is going to be faster. And so here's the explanation part. So if we look at our equation here, so as we increase temperature, the particles have a lot more kinetic energy. So they're moving around a lot more, and so that means they've got a better chance of them colliding successfully to allow a reaction to happen. So this means this increases the rate. If we increase the temperature, the rate increases. But the concentration of the substances remain constant. Increase in temperature doesn't mean you get a higher concentration of either of them substances. So you can see here, if we increase the rate of reaction or increase the temperature, rate increases, so this goes up, but these numbers here remain the same. So to make these two equal, then the value of K must therefore increase, okay, to make sure the equation still balances. So you can see here, this is the relationship between the rate constant of K and rate of reaction. Okay, so what we're going to do now, so we've got our rate equation, we're now going to calculate rate, okay, using this equation here. Okay, so using that rate equation, we can calculate the rate of reaction. So let's have a look at this example here. So the following reaction was carried out in a lab. So we've got nitrogen monoxide reacting with oxygen to form NO2. And so it's found that the reaction's second order with respect to NO and first order with respect to O2. Now what we have to do is calculate the rate of reaction given the concentration of NO is 3 times 10 to the minus 3 and O2 is 1 times by 10 to the minus 3. Obviously they're all moles per decimeters cubed. And the rate constant K is 700,000 mole to the minus 2 dm6 s to the minus 1. Okay, so what we're going to do is the first thing we should do with this is write our rate expression. So our rate expression is rate equals K NO squared O2 to the 1. Okay, so we've got NO. The reason why this is a 2 is because in our rate expression, our equation, we have 2 lots of NO, so therefore it must be to the power of 2. And for oxygen, we have a power of 1 because we only have one of them in our original equation. You don't have to show the 1. Effectively, the 1 can just be dropped from there because having anything in there means it will be first order. Okay, so basically what we're saying is that NO is first order. Sorry, so there it is there. So it's second order with respect to NO. That's what I should say there, not in the equation here. That I'm thinking of equilibrium constant. So just ignore that bit. So we're told that second order with respect to NO and first order with respect to O2. Apologise for that because I'm thinking it's equilibrium, but it's not. It's rate equation. So if you see my equilibrium video or video on equilibrium, you'll see what I'm talking about there. So they've told us the order, okay? Because obviously you can't work out order just from the equation. Right, so then what we're going to do is we're going to substitute our numbers in there, okay? So rate equals 700,000 times by 3 times 10 to the minus 3 squared, okay, multiplied by 1 times 10 to the minus 3. So basically, we've put all our numbers in there, but remember we're squaring the NO bit because we've been told it was second order. So then the rate of reaction, so rate is 6.3 times by 10 to the minus 3. Moles per decimeters cubed per second. So fairly straightforward. All we're doing is just putting our numbers in and getting our answer from there. So that's pretty straightforward. Okay, so what about if you want to work out the rate constant, which is K? So obviously we can use that same expression to work out the rate constant. Okay, so here's an example here. So a slightly different example. So the following reaction was carried out in a lab, and you can see it there. And we're going to calculate the rate constant for this reaction given that the order with respect to NO is second order and 0 order with respect to carbon monoxide and oxygen. And the concentration of all reactants is the same, so it's 1.5 times by 10 to the minus 3 moles per decimeters cubed, and the rate of reaction is 1.17 times by 10 to the minus 3 moles per decimeters cubed. So pretty straightforward. We write down our rate expression first. Now notice that carbon monoxide and oxygen is not included in this rate expression. This is because they're 0 order. And because they're 0 order, obviously they don't appear in the rate expression. So the only thing that we include in there is the NO, which is second order. So that's why we put the 2 on the side there. So then we need to rearrange this equation to make K the subject. So that's what we do there. So K equals rate over NO squared. We then put our numbers in. There they are. Okay, 1.17 times by 10 to the minus 3 divided by 1.5 times by 10 to the minus 3 squared. And then we get our value of K to be 520. Now remember, the units can vary depending on what we're reacting it with. So we need to work out our units. So very straightforward. All we have to do is we add. So we just take the units of each of these and write them in the equation. So rate is moles per decimeter cubed per second. And NO, because this is squared, we write the concentration twice. And then what we're going to do is basically cancel out units top and bottom. And then any units remaining, we then lift them onto, so if them on the bottom, we invert them onto the top and we change the sign. So let's have a look. So we can cross them off there. So you can see here that we've got an S to the minus 1 at the top, so that's fine. But we've got a mole per dm cubed at the bottom. Okay, now when we invert that, we change the sign. So that's going to be mole to the minus 1, dm to the 3. So that is our answers for the units. Okay. Okay, so let's look at some rate graphs. We looked at the graphs already from when we worked out rate from practical experiment, and then we plot our results in there. So that may be concentration against time, for example. So how the concentration changes over time, we plot that graph and we get them from there. So that's fine. What we can do is take them graphs and take rate from them graphs to work out a different set. And actually, if we do what we call a rate concentration graph, this can actually help us to identify the order with respect to that reactant. So for example, we can work out if something is 0 order, if it's first order, or if it's second order. So let's have a look at some of these examples. Okay, so a rate concentration graph is created by knowing the rates. Remember how we worked out rate from the previous graphs. So that was concentration against time, and we take the gradient of that, and that tells us the rate of that reaction. Now on that curved graph, we can take the rate at different points. So we take multiple rate values from that graph, and effectively we're going to take them rate values and put them in a new graph called a rate concentration graph. Okay, and what we're going to try and do is then going to use these graphs to work out order. What I don't want you to do is to get them mixed up. They're very different graphs. One's a rate concentration graph. The other one is a concentration time graph. So concentration time is what you get directly from experiment, and then we use that to work out the rate, and we plot a new graph called rate concentration. Okay, so let's have a look at the first example here. We're going to compare the two side by side. So the rate, you can see as concentration, so you can see as the concentration changes, so the concentration is decreasing equally against time. So this is what you would plot directly from experiment. Now, if we take the rate at each of these points on here, the rate is going to be constant. The rate's not changing here because it's a straight line. So you can see here we can get a rate concentration graph to be a straight line, and that means it's 0 order. Okay, so change in the concentration of this has no impact on rate. So let's look at another one. So this one is, you can see, is first order. Okay, so you can see that the rate on this shallow curve here changes in equal amounts. So if I measure the rate at different points on this curve, I'm going to get a graph like this, which is going up as a straight line. So this is first order. So this means that changes in concentration of air here means that whatever that change is, it's going to increase the rate equally, okay, or decrease it depending on which way it's going. In this case, it's an increase because the graph's going up. Okay, and the last one is this one. So this is where we've got a steeper curve. Okay, so it's a lot sharper curve, as you can see here. So when we plot the concentration, the rate across these the different points in the curve, we get this graph here, and this is second order. So this means by changing the concentration, say if we double the concentration of A, we quadruple the rate. So as a second, a squared proportional effect. Okay, so ideal rates, like I say, we've looked at initial rates, not ideal rates, initial rates. We've looked at initial rates already, and we know that initial rates is the rate the rate of the reaction right at the start. Okay, so initial rates is a good way of working out the rate equation that we've just seen there for reaction. So let's say we want to work out the rate equation for A plus B plus C will give D plus E. Okay, remember we can only work out the rate equation by actually doing an experiment. So we're using a generic example here. So what we're going to do is repeat the experiment several times, but changing the concentrations of A, B, and C one at a time for each experiment. So we're going to keep changing it, okay? And what we want to do is we're going to find out the effects of changing the concentration of each one on rate, okay? So we've gone through that a little bit already, okay? And so to work out the initial rate for each experiment, we calculate this using the graph shown before. So we'd seen the graph where we had our concentration against time, and then we can take the rate right at the start, or we can use our clock reactions, and our clock reactions give us the initial rate, and we can then use that to work out our rate expression, our rate equation that we've just seen just before. Okay, so we're just piecing initial rate and rate equation together. We're bringing them all together to do something useful with it. So this is why this bit is being pulled back in again. So we record the concentrations of reactants used for each experiment and their initial rates in a table, okay? And then from this we can then work out the orders with respect to each reactant in the rate equation, okay? So we're going to do our experiment, we're going to change the concentration of each substance, and we're going to monitor the rate of reaction, and we're going to write that down as an initial rate. Okay, so we're going to do this practically. Okay, so what we're going to do, I think the best thing to do with this is when we're bringing in initial rates and rate equations or rate expression that we've just seen before, we need to actually apply this into a practical sense. So this is what we're going to be looking at now. So like I say, initial rates is a great way of working out the rate equation for a reaction. So let's have a look at an example here. So here's some experimental data for the following reaction. So we have 2NO plus Cl2 will give 2NOCl. You can see that's being produced there. So give the rate equation and calculate the initial rate for experiment 4. So you see we're bringing in these two elements together now, okay? So we've got our data table here. So just before we kind of move on and start and work this out, just to kind of navigate you around this table here. So you might get one of these in the exam where we've got experiment 1, 2, 3, 4, and basically we've repeated this experiment 4 times. But what we've done is we've altered the concentrations of NO and Cl2, and we've monitored the initial rate of each of these. But the problem is we don't know the initial rate for this one here, so we need to work that out. And obviously we need to work out the rate equation as well. Okay. So the first thing we need to do is we need to work out order with respect to NO. Okay, so that's the first thing we need to do. We need to work out what each of these substances, what is the order for each of them. So work out for NO first, and ideally we need to compare experiments where the concentration of NO is changing and the concentration of chlorine is constant, because if there is a change of rate, we know that it's only because of the concentration of NO and not Cl2. Okay, so the experiments here that we're looking at is experiments 1 and 3. And the reason why we're picking 1 and 3 is really simple, because the concentration of NO is changing here, so it's going from 0.2 to 0.8, but the concentration of chlorine is remaining the same, as you can see there. So you've got 0.1 to 0.1, so any changes in rate has got to be because of NO, not because of Cl2, because obviously that's remaining constant. So experiments 1 and 3, like I say, concentration of nitrogen monoxide has quadrupled, so it's multiplied by 4, and the initial rate has also quadrupled. So with respect to NO, it is first order, okay, so it's a proportional change. So secondly, we need to work out order with respect to chlorine, which is Cl2. And ideally, again, just like we did before, we need to compare experiments where chlorine is changing this time and nitrogen monoxide is remaining constant. So we can see here we can use experiments 1 and 2 for this. There we are. Okay, because you can see that the concentration of NO is now remaining constant, but the concentration of chlorine is now increasing. So any change in rate has got to be because of chlorine and not nitrogen monoxide. So experiments 1 and 2, you can see chlorine has trebled and the initial rate has trebled as well. So therefore the order with respect to chlorine is actually first order. So now we can write our rate equation and we've got the answer to our first bit. So our rate equation is going to be this. So rate equation is rate equals K, the concentration of NO, and then the concentration of Cl2. Both of them are first order with respect to both of them substances. Excuse me. Right, so we haven't quite finished there because remember, we need to work out the initial rate as well. So we've worked out the rate equation, and now we need to work out the initial rate, which is down here. Okay, so let's carry on. So bring back this information that we had last time, okay, and I've just brought in our rate equation that we've seen there. So this is fairly straightforward now. This is the kind of easier bit. So first of all, we need to calculate K. That's what I would recommend, okay? Calculate K first, and then what we need to do is then pick any experiment in there with all the data complete. Once we've got all the data, once we've found a row with all the data in, we then work out K, okay? Because all of these, we assume that all these experiments are done at the same temperature. Remember, this is one of the assumptions that we're making. So all these are done at the same temperature, so we can say that K is the same value for any of these experiments here. Okay, so let's work out K. We're going to use experiment 1, and so we're going to use the data in here. So rate equals K, concentration of NO, concentration of Cl2. We rearrange the equation to make K the subject. We then put the numbers in, 0.63 divided by 0.2 times 0.1, and then we get the value of K to be 31.5 moles per decimeters cubed per second. Okay, so we put all our numbers in there and we get the value of K. Now K is the same, like I say, for all of them. So now we're going to use that value, use the rate equation and our calculated value of K to work out the rate in experiment 4. Okay, so put all the numbers in. So rate equals K NO Cl2. So the rate equals K, which is 31.5. We've just worked that out. That's why it's useful to work this out first, because we can just put all the numbers in. Concentration of NO in this experiment here is 0.5, and it's the same with chlorine as well. So put all the numbers in, and our rate is 7.88 moles per decimeters cubed per second. Okay, so that is the figure that goes in there. So you can see here that we've worked out two different things here. So we've worked out the rate equation first, and so using the initial rates method, which can be determined by a clock reaction, as we've seen before, and we've worked out the rate of reaction as well from our equation. So that's fine, but the exam board may give you one that is a bit more difficult than this, and I'm going to go through this example because I think it's important. This is it's quite tough. There's a lot of things to think about here, but relative to the one I'm going to show you now, it's actually fairly straightforward. And the exam board may give you one like this, but don't panic. I've got a pretty decent method that kind of explains how to work this out. You might have a different way of doing it, but if you've seen any of my other videos, I like to keep things methodical and keep it broken down and detailed so you can see everything. Okay, so here's the difficult one here, okay, for the initial rates method. So sometimes your rate tables don't have a substance where the concentration remains constant, okay? Sometimes it changes, which is a real pain. And actually, practically, if you were doing a practical, you would never set it up the way I'm going to show you here, okay, in terms of your practical. But the exam board, what they're wanting you to do is they're wanting to test your knowledge. They want to test to see how much you really can, deal with these tables by giving you obscure data. Okay, so let's have a look at this example here. So a reaction occurs between A and B, and the experiment was repeated 3 times, varying the concentrations of A and B. And we've got to give the rate equation for this reaction using the data below. So we're not going to work out the initial rate in this example. We're just looking for the rate equation. So let's have a look at our table. Let's have a quick explore of our table here. And you can see we have repeated it 3 times. We've got the concentrations of A and B, and then we've got our initial rates for each of them there. Okay, and we want to work out our rate equation, our rate expression. Okay, so the first thing we need to do is work out order with respect to A. And ideally, we need to compare experiments where the concentration of A is changing and the concentration of B is constant. So exactly the same as what we've done before. So you can see here that if we look at 1 and experiment 2, that works because we can see that the concentration of A is changing. That's fine. The concentration of B is remaining the same. So we then look at the values and we see that the concentration of A has trebled and the initial rate has actually increased by 9. So it's increased 9 times. So A is second order. So with respect to rate, A is second order. Okay, so that's fairly straightforward. So don't worry, you think, well, that was easy. I've just seen that before. And this is where it gets a little bit tricky. So now we need to work out the concentration, so the order with respect to B. Now, this is tricky as A is changing in each of the experiments. So A is not constant. This is what I'm saying. If you were to do this practically, you would never do it where you're changing A all the time. With the exam board's just testing your knowledge. They're just testing what you want to do. Okay, now, you might have a different method of doing this. You might be taught a different method. That's fine. There's no right or wrong way of doing this. This is a method that that I use because it helps to kind of see what's going on. It makes it really clear, I hope, anyway. But as long as you get the same answer as what I'm getting, then you should be fine. So what we're going to do is we're going to add another column at the end showing the rate, what the rate would be if we only changed A. Okay, so we're going to look here at experiment 2 and 3. Okay, and we can see here that the rate of A, the concentration of A, is doubling. Okay, so you can see that it's gone from 0.45 to 0.9. So the rate, in theory, if A only had an impact, and if we just ignore B for the time being, just imagine B doesn't exist, then the rate would quadruple. So effectively, instead of it, so you can see the rate here is 3.78 times by 10 to the minus 3. You can see it there. So if B had no impact, then the rate would be this. Okay, 15.1 times by 10 to the minus 3. Okay, this is it written down here. Okay, so that's what it should be in theory. Now we can see in practice the rate isn't that. So B must have some kind of impact on rate, because if B didn't have any impact, in other words if it was zero order, then the rate in here would be equal to that rate there. Okay, because this is showing the effect only to A. So then what we'd do here is you can see there's a difference in the rates, and you can see the difference. We just work out the difference here, and this is half. Okay, so the difference, the rate has actually been reduced here by a half. Now this has been reduced by a half, and so has the concentration of B has been reduced by a half. So what we can say is that with respect to B, this is first order with respect to B. Okay, because we can see here that the difference in the value here is half. Okay, so that's the theoretical value if A only existed, but B is having an impact. So the difference here is a half, and what's causing this rate to be half that value is because B is halving as well. So this is obviously first order. Okay, so I use that last column there to help me kind of work out, what it would be if B had no impact, and then what it would be, obviously then comparing the initial rate with that theoretical rate in that last column that I've drawn there. So the final thing we need to do is obviously write our rate equation, and our rate equation is going to be rate equals K, A squared, and then B. Okay, so that's how you'd use the initial rates method, which we talked about, just to summarise, because we've covered a lot of stuff there, okay? So we've covered, and we're about a third of the way through the video, so 2/3 of the way, sorry, through the video. So you can see here that we've got, we've looked at initial rate method. We've looked at how we can calculate initial rate using the clock reactions. We've looked at the rate equation, and we've looked at orders and how, first, second, 0 first and second order, and we've looked at the rate constant and what we can do with the rate constant. And then what we've done is used all that information that we've done there and applied it to this initial rates method, where we've been given a set of data and we have to work out the order of orders of reactions, and then hence write our rate equation. So we've looked at that bit. So now what we're going to do is kind of break away a little bit from that and look at something called half-life. Okay, so half-life is linked with orders, but we're just observing something slightly different here. So half-life is T1/2 is the same is the time it takes for half of the reactant to be used up. Okay, now if any of you do physics, you'll be quite familiar with this, because half-life is quite an important part of physics. But for those who don't do physics, or I'm not sure what half-life is, obviously I'm going to go through it on here. So half-life is this. So we're going to pull up a graph here, which is concentration of a substance, and this is decreasing over time. So there's obviously a reactant being used up, and it's over time, which is measured in seconds. Now, half-life can be calculated using this type of graph. It's a concentration time graph. So this type of graph is effectively developed from practical, straight from a practical. You put your results in here, so how concentration is changing over time. Okay, so this is showing the decomposition of hydrogen peroxide, as you can see. Now, to work out half-life, what we're going to do is draw a few guidelines on this graph here. So the graph shows here it takes 200 seconds for half of the hydrogen peroxide to decompose from 2.6 to 1.3 moles per decimeters cubed. Okay, so you can see here it takes 200 seconds, that's it there, that's how long it takes for half of this to decrease. Okay, so that's the first bit. We're then going to say, right, well, how long does it take for this to halve? So we're going to do exactly the same. Let's put that in. Okay, so we can pick any concentration value. Sorry, I'll come into that in a minute. I'm jumping ahead of myself. So we can pick any concentration value on the graph to find out how long it takes for it to halve. Okay, so we can pick any one on there. So let's have a look. So we're going to do this one. So again, that's half of 2, so that's going to be another 200 seconds, as you can see. Oops, there we are. Okay, and you can see that the decomposition of hydrogen peroxide actually takes 200 seconds to halve its concentration, so the half-life actually remains constant with all of this. Okay, so you can see there the half-life is remains the same as we go in this example here as the reaction proceeds. So what we can do with that is we can then identify the order of reaction from these graphs as well. So you can see that a rate, so the rate on a straight line graph is constant, so change in the concentration of this doesn't change the rate, and so the half-life actually decreases in this example. So let's have a look. Okay, so there's your examples there. So you can see the half-life is actually declining as we're going along. So that graph there is telling us it's 0 order. Okay, so this is just the same type of graph you've just seen before there. So let's have a look at another example. So this one is a first order reaction. We get that curve. This is the one that we've seen before. And actually the half-life is constant, just like that graph that we've seen there before. So there we are. Okay, so you can see the values of the half-lives are constant. So anything like that is a classic sign of a first order reaction where half-life remains the same. And then finally, a second order reaction is where the half-life actually increases. So we've got a much steeper curve, as you can see there. So let's have a look. So there it is. Okay, so you can see the half-life is increasing as we go down this curve. So an increase in half-life is second order, a constant half-life is first order, and a decrease in half-life is a 0 order reaction. Okay, so make sure you're familiar with them graph, because you might be given a graph like this or asked to plot a graph and work out the half-life of it. And we're going to look at the equation using half-life in the next slide, but you are expected to be able to identify whether it's 0, first or second order from them graphs using half-life, or comment on them about half-life. Okay, so half-life can also be used to work out the rate constant, remember that's K, of a first order reaction, and that's what we're going to be looking at here. So that half-life graph can be used to calculate the rate constant, as we've seen there. So we're just bringing this graph back again that we'd seen before, and you can see here this is a concentration time graph showing a first order reaction. Because remember, it's this classic curve shape here where the rate. So remember the half-life is constant along the bottom here. So that's the same one we'd seen before. So this is the decomposition of hydrogen peroxide. Okay, so you can see that. There we are. Okay, so the concentration of H2O2 from 2.6 to 1.3 is 200 seconds. And then if we do exactly the same as what we'd seen before, that's going to be 200 seconds as well. So that confirms that it is indeed first order reaction. Okay, so the half-life for first order reactions, the half-life is independent of concentration. So each half-life will be the same length in these first order reactions. So to work out the rate constant then from this graph here, then K is ln2, so that's the natural log of 2, natural log times 2, divided by T1/2. So T1/2, remember, is your half-life. The units for this is s to the minus 1. So what we're going to do is use the information in this graph to work out the rate constant. So rate constant, which is K, is calculated as K equals ln2, so ln times 2, divided by 200 seconds, because that is our half-life in this example here, and then we get a value of K of 3.47 times by 10 to the minus 3, s to the minus 1. Okay, so be familiar with the half-life bit here. So be familiar with working out the half-life from the graph first, but also being able to look at these types of graphs and determine whether it is 0 first or second order. And then obviously we've got to be able to work out rate constant as well from these graphs. So what you can see here is there's various different ways in which you can work out the rate constant. Okay, so what we're going to do is we're going to break away into a new section here, and this is called the Arrhenius equation. Now, you might, as soon as you hear that word, you think, oh, not the Arrhenius equation. Okay, it's massively complicated. It looks horrendous, absolutely horrendous equation. I'm going to try and simplify this as much as I possibly can. Okay, so let's have a look here. So the Arrhenius equation links activation energy and temperature to the rate constant, which is K. All right. So we're going to be looking at two different ways in which you can work this out. One from just using the calculation, the equation, and one using plots, so Arrhenius plots. So we're looking at two different ways here. And the Arrhenius equation is this. So K equals AE to the minus EA over RT. Okay. So let's look at what these different parts mean. So K is our rate constant. We know that. We've seen that already. A is something called our Arrhenius constant, okay, which is that A there. Now E is an exponential. So you might see that in your calculator. It's an E. It says E on it. So look out for the EX button on the calculator. So that is your exponential button. Those who do maths may be familiar with that. If you don't worry too much about this. I'll break this down. We'll get rid of that and simplify it. EA is the activation energy, which you will have seen in year one chemistry. R is your gas constant, which is 8.31 joules per Kelvin per mole, and T is your temperature, which is in Kelvin. So these are all the different parts of the Arrhenius equation. So there's some important points that we need to be aware here. So the first important point, so point number 1, is the activation energy, EA, gets smaller. The rate constant gets bigger. So as that gets smaller, the activation energy, the rate constant K gets larger. Okay. So the reason why is because the activation energy drops. So this means that the activation energy drops the rate of reaction as the rate of reaction increases. Okay. So you've got many more particles that have enough energy to react when they collide. Okay. So if we think about it, so if the activation energy, so you imagine your activation energy in your energy profile graph, as that drops, you need less energy to actually get these for successful collisions to occur and to produce your product. Okay, so activation energy, as that gets smaller, the rate constant K gets bigger. The second important point is that as we increase the temperature T, the rate constant K increases. So increase the temperature, K increases as well. So the reason why is that obviously when the temperature increases, the particles have a lot more kinetic energy, so therefore they are moving around with a lot more energy. They've got a higher chance for successful collision, and so therefore they are more likely to produce your your product much quicker. So therefore the rate constant K increases as a result. Okay, so we're just talking about the constants here, so rate constants increasing. So we're looking at what affects that. So EA gets smaller, rate constant increases. As temperature increases, rate constant increases. Okay, so be prepared to know them particular relationships and why, and explain them. Okay, so we're going to look at the calculation using the Arrhenius equation. So we're going to look at it first by using the calculation first, then we're going to look at plots later on. So the Arrhenius equation is great for calculating the activation energy or the rate constant. So for example, calculate the activation energy in kilojoules per mole of a reaction at 330 Kelvin, a rate constant of 1.3 times 10 to the minus 4 per second, and we're assuming the Arrhenius constant is 4.55 times by 10 to the 13, and the gas constant is 8.31. Okay, so we've got a lot of information in there. So what we're going to do is we're going to write out our Arrhenius equation first. Okay, so our Arrhenius equation is K equals AE minus EA over RT. What we're going to do is we're going to make it a bit simpler. Okay, so this exponential bit we can actually get rid of, and we can do that by simply taking the natural log of both sides. Okay, so we take the natural log of this, which is going to be ln K, and then we're going to have ln A, because we're taking the natural log of A, and this E bit disappears, and we basically just have minus EA over RT. Okay, so this gets rid of this E part, and we can actually get a much more simplified equation. So that's what I would suggest doing first, is simplifying that first. And then what we need to do is rearrange our equation. So we're going to start to move EA to one side of the equation, because that's what we want to work out is the activation energy. So what I've done is we've moved this across to this side, so it's EA over RT. So basically we're adding this bit. So we add it to this side, we add it to this side. And then the lnk bit is moving across the equals, and we put a minus in front of that because we're doing the opposite. So if you're quite comfortable with maths, then this might seem straightforward, but just trying to explain where these negatives and where this bit comes from is just important for people who are maybe not so confident at maths. Okay, so now what we have to do is then multiply both sides by RT to get EA on its own. So if we multiply, because this is divided by RT on this side, so if we multiply this by RT, we basically cancel that out, and we put multiply RT on this side. So now, finally, we have EA on its own. Okay? So now what we're going to do is we're going to put our numbers in. Okay, we're going to substitute the numbers in. So you'll need the ln button in your calculator, so look out for that. Okay, you'll see that there. So we're just going to put the numbers in here. So you can see that we've got ln A, which we've been given, which is 4.55, that's our Arrhenius constant, minus natural log of K, which we've been given as well, which is there, that's our rate constant, multiplied by 8.31, that's our gas constant, and temperature is 330 Kelvin. So what I'm going to do is just simplify this a little bit further. So there it is. So all I've done is I've done this to get that. I've done this to get that. And then obviously I've left this bit at the side. So I've just taken the natural log of both these numbers just to see what that is. Okay, so then we're going to put all them in our calculator, and we get a value of EA, which is 110,781 joules per mole, or 111 kilojoules per mole. Okay. Now, I have done a video on this where I go through it in a lot more detail on the whiteboard, go through a similar example, same method, but just go through it. So, by all means, have a look on that. Just click on the card above, and you'll be able to have a look at it there. Okay, so now what we're going to do is look at Arrhenius plots, okay, and we're going to calculate the activation energy in this example here. So, an Arrhenius plot can be used to find out the activation energy and the Arrhenius constant. Okay, so we can work out both here. So in this example, we're going to look at calculating the activation energy. So we can use the Arrhenius equation that we've seen. That's the simplified one where we've taken the natural log of both sides. And we're going to plot ln K against 1 over t, and then we're going to draw a line of best fit, and that gradient, or that line, the gradient of that line, represents minus EA over R. And then what we can then do with that information is then calculate the activation energy and the Arrhenius constant as well. So here we're going to look at the activation energy in particular. So here's our example graph, and you can see there, so they might give you a graph like this in the exam. We've got 1 over t and ln k on this side, and we've got our gradient here, our line there. Okay, so remember, there we are. Okay, so there we are. So remember, your gradient is change in y over change in x. Okay, so that's how we work out our gradient. So we're going to work out the activation energy here. So to work out the gradient, we do minus 1.1, which is there, divided by 0.1 times by 10 to the minus 3. Now the reason why this is times 10 to the minus 3 is because the units on the top here tell us is times 10 to the minus 3. Always look at the units there. If you just put 0.1 in there, you're going to be out by considerable amount. So you've got to remember, look at the units in the graph, make sure you put them in there. Gradient here is minus 11,000, so minus EA over R, because that's what the gradient represents, remember, is minus 11,000. Okay, so what we're going to do is rearrange this equation. So we're going to move EA to one side of the equation here. Okay, so that's what we've got there. So EA, which is this bit, equals, so that's minus 11,000 or minus 11,000 times by 8.31, because that's our gas constant. Okay, and then we should have EA to be 91,410 or 91.4 kilojoules per mole. And again, I've done a video on this as well, looking at Arrhenius plots. Just click on the card above that pops up on the screen, and you'll be able to have a look at it there. Go into it a little bit more detail. Okay, so we're going to keep that graph there, but this time we're going to work out the Arrhenius constant, which is A. Okay, so we worked out the activation energy. We're now going to use the same type of principle, but work out the Arrhenius constant. So the Arrhenius constant, all we have to do is just substitute the values of the gradient and the coordinates of any point on the line into the equation. Okay, so we've got ln k equals minus EA over RT plus ln A. Okay, so we've put all that information into our equation there. Okay, so we've got our full equation there. Okay, just like what we've seen before, the simplified version without the exponential bit in. So we're going to substitute into the equation using the coordinates circled, which is there. Okay, so just the mathsy bit, what I've done is I've restructured this equation to be a straight line equation. So remember, equation for a straight line is y equals mx plus c. Okay, y in this equation is your y-axis. This is the main point here. X is your x-axis, which is obviously over here, and m is your gradient, which is this part here. So obviously we're going to look at the gradient. So what I've done is I've just rearranged this equation to fit the same way as the straight line. So that's going to be ln k minus EA over R times by 1 over t plus ln A. Okay, because we have a straight line graph, so that's where I've got this from. So all I've done is I've put in the coordinates here. So y is minus 4. Okay, which is this bit here, yeah. M is your constant, your gradient, sorry, which is minus EA over R. So that's minus 1.1 divided by 0.1 times by 10 to the minus 3. Okay, because we've got the figures there. So this was taken from the previous slide, and then multiply that by your x, which is 33.1 times by 10 to the minus 3. So that's the value of x there. That's that value. And then ln A is the value of C. That's the bit we want to work out. So then what we have to do is rearrange that, or simplify that, should we say. So you can see our gradient was 11,000. That was taken from the previous slide. Okay, that's how we worked out our gradient before. And then that's the bit that we've just worked out there. And we're going to simplify that again. I'm going to multiply them two numbers together, and we get 34.1. So I'm just breaking it down so you can see exactly what's going on here. So it's minus 4 equals minus 34.1 plus ln A. And then we're going to make ln A the subject because we want to work that out. So we put ln A equals minus 4, okay, plus 34.1. Okay, so that's what we need to do. And then we add them two numbers up and we get the value of ln A, which is 30.1. Now, we just want to work out the value of A, which is the Arrhenius constant. So to get rid of the natural log, we do the exponential. So this is when you do have to use the exponential button. So you put the E in there, and then we put 30.1 on the top. And then we should finally get the value of our Arrhenius constant to be 1.18 times by 10 to the 13, dm3 mol to the minus 1, s to the minus 1. Okay? So there's a lot there, isn't it? Okay, so just make sure you're comfortable and practice these types of questions. Make sure you know how to work out the Arrhenius constant, familiarize yourself with y equals mx plus c, and make sure you be able to work it out using the equation as well, in other words, without using your graph. Okay, so what we're going to do is we're going to look at the last section of this video, or the last sections, should I say, which is rate determinant steps, your multi-step reactions. Okay, so the rate determining step is the slowest step in a multi-step reaction. Okay, so a lot of reactions proceed via not just via one step, but by quite a few steps. So most reactions, like I say, they occur via many steps, but there's one step in a multi-step reaction that is the slowest step, and that it determines the overall rate of your equation. Okay, so if we can do something at that rate determining step, then we can speed up the rate of our reaction overall. Now I'm going to use an analogy here, and I'm going to use an analogy because I like bacon. So I'm going to use an analogy of a bacon example here. So how would you make a Victoria sponge? And the Victoria sponge is actually made in a few different steps. You don't just take your ingredients and get cake at the end. You have to do things to it to make that. Some processes are quicker, some are slower. So you can see here, step 1 is to gather all your ingredients. It takes about 10 minutes to do that. Step 2, to weigh them all out. Step 2 is to mix the ingredients, about 5 minutes. Step 3, we chuck it in the oven and allow it to cool. It takes 1 hour and 30 to do that. And then step 4 is we dust with icing and add the filling. It takes about 5 minutes to do that. So you can see that this is a multi-step process. There's numerous steps that we have to take to make this Victoria sponge. So you can see here the cake takes a total of 1 hour and 50 to make, so about 1 hour and 50 to make the whole cake. The rate determinant step, so that's the slowest step in this reaction, is step 3. Okay, so if we are to reduce the overall time significantly, we need to speed up step 3. We need to do something with step 3. So for example, in the cooling phase, we could add it to the fridge and that will cool it down quicker. Or we can use a fan oven. A fan oven means we can probably cook the cake quicker than if it was in a non-fan oven. So by using this method, or by using this kind of analogy, you can kind of see that, okay, there is a step that's slower, and if I put that in the fridge, my overall time is going to have a much greater difference by altering step 3 than altering any of the other ones. So in chemical reactions, we have a similar type of reaction. We're going to bring it back to chemistry here, because all this talk cakes make me quite hungry. So in chemical reactions, we have exactly the same, except to speed up reactions, we don't put it in the fridge, or we don't use a fan oven. Instead, we're going to add a catalyst, which will speed up the rate of reaction, or alter the temperature, which may impact that rate determinant step. So we have other tools at our disposal, which we can use to speed up the rate of reaction. So the rate equation, very, very important here. So reactants that appear in the rate equation affect the rate of reaction. Okay, so these reactants or substances derived from them, so if they're made from something else, must appear in the rate determinant step. You must remember that, because the examples I'm going to go through in the next couple of slides are going to be using that principle there. Okay, so I'll just go through that again. So reactants that appear in the rate equation will affect the rate of reaction. So if they're in the rate equation, it'll affect the rate of reaction. Okay, so these must appear in the rate determinant step. Okay, so that's very, very important. Okay, so substances not in the rate equation won't be in the rate determinant step. Really straightforward. So that rate determinant step must have the rate expression in there. Okay, so it's not just reactants that can appear in the rate equation. Catalysts. Okay, so catalysts can as well. So catalysts, as you can see, are not in the rate, not normally in an equation, because they're not actually a reactant, but they do have an impact on rate of reaction, and sometimes the amount of catalyst in there can have an impact as well. So you can see if I had to create a rate equation for this, the rate equation for making a cake could be rate equals the concentration of bake in the oven and cool afterwards. Okay, because that is the rate determining step, so that must appear in the rate equation. Okay, right, so let's look at some specific examples here. Obviously, we've looked at baking a cake. We're going to have to bring it back to chemistry, unfortunately. But just have that analogy in your mind when you're looking at these examples here. Okay, so the rate equation can be found from a multi-step reaction. So we're going to look at this multi-step reaction here. So we're going to deduce the rate equation for the following generic reaction steps. So step 1 is A plus B will give 2C. That's a fast step. Step 2 is 2C plus 2C will form D, and that's a slow step, and then D plus C will form F plus G, and that's a fast step. So the overall equation for this is A plus B plus E will give F plus G. Okay, so we've got all these different reagents here, and we can see that this reaction here actually proceeds via 3 steps, with step 2 being the slowest step. So the first thing we need, or the first thing we know, should I say, is that the rate determining step is step 2, because this is the slowest step. So that is your rate determining step. Okay, so one of the reactants, and you can see there, is C. So this must appear in the rate equation. It absolutely must. Remember, if it's in the rate determining step, it must be in the rate equation. So notice the 2 next to it. This tells us, this is quite clever, this tells us it's to the power of 2. In other words, it's second order with respect to C, because we know the mechanics of this. Okay, so C is an intermediate, okay, which we know because it's formed in step 1, which is formed or derived from A and B. And so for this reason, both A and B must also be in the rate equation, because C is derived from A and B. We wouldn't have C if A and B weren't there. So A and B must also be in the rate equation as well, because it's derived from it. So there are only one of A and B, and so the order is first order with respect to A and B, okay, because there's only 1 mole of each. So now what we can do is write our rate expression, so our rate equation, which can be deduced. And so our rate equation is rate equals K, concentration of A, concentration of B, and the concentration of C squared, because it has that 2 in front of it, okay? Now, what's really important here, I think, well, hang on, where's C in that equation? So our overall equation doesn't even have C in there, okay? That's not a mistake. What we've got here is obviously a catalyst, because it doesn't appear in the overall equation, but C is clearly a catalyst, and we know it's a catalyst because it doesn't appear in this overall equation, but it is in this rate determining step. So they might ask questions like that, so don't be worried if you think, well, that's not in the equation, where's C come from? It is there, it's just a catalyst, of course. Okay, so let's look at some more examples or further examples of this. So the rate determining step can be found from the rate equation as well. So let's have a look here. So we've got the overall reaction. So we deduce the reaction of the following. So obviously this is not generic. This is a proper reaction. So we'll remove the word generic. I'll get all that changed as well. So if you are going to get a hold of these, then I'll change all that. But step 1 is nitrogen monoxide plus nitrogen monoxide will form N2O2. Okay, and then N2O2 plus O2 will form 2 lots of NO2. And we've been given our rate equation here, which is rate equals K NO squared times by the concentration of A. But notice we haven't been told which one's fast and which one's slow. Okay, so we need to work some of this out. So the first thing to notice here is the ratio of molecules we are looking for. Okay, so the rate equation is saying we need to look for 2 NOs and 1 O2, because it's to the power of 1 for that one. So looking at the reaction steps, as you can see here, there isn't a single reaction step which has that ratio in there. So 2 molecules of NO and 1 of O2. There isn't a single one step. There isn't one step in there that actually contains all of that. So what we have to do is we have to kind of play a bit of a game here, and we're going to play chemical bingo. Okay, this is the fun bit. So what we need to do is we need to start from step 1. Okay, and we need to score off the molecules or atoms needed to match the ratio in that rate equation. Okay, and then what we do is we stop once we've accounted for all of them that we need. Okay, and so this step, where the one that we stop at when we've accounted for all the atoms, all the elements or molecules, whatever it is, in our rate equation, then that is the rate determining step, and we shout bingo. Well, I wouldn't shout bingo in an exam because it might look here. But just do it in your head. Right, so, and bingo, because you've got the marks as well. So we have 2 lots of NO, and so we score them off, but we still have an O2 to get, so we continue to step 2. So let's score them off. So there it is. Okay, so we've got that one. So then we need to keep going, because we need an oxygen. We haven't got an oxygen yet. So step 2, we have the oxygen molecule. There we are in step 2, as you can see there. There's the oxygen. So we have that in step 2. We've now accounted for all our molecules, so that is when you shout bingo. Okay, so what that means, bingo means that you've identified your rate determining step. And so your rate determining step is step 2 in this case. Fairly straightforward. Don't look at these and think, oh crikey, that's really hard. It doesn't have to be, okay? You might have been taught a different way. You know, as long as you get the same answer, it doesn't really matter. You know, I just like to do it this way and score them off and make sure that you can work out what your rate determining step is. Just makes it a little bit more interesting when you're playing bingo in an exam. Right, okay. So still sticking on to rate determining step. So this time we're actually going to deduce a reaction mechanism from the rate determining steps. The reaction mechanism can be found from that. So the following reaction occurs via 2 potential mechanisms. Okay, so the first mechanism is that. In other words, it just goes in one step. There's no multi-step here. The second example, there's the first example there. Okay, and the second example is actually where it goes via 2 different steps, as you can see there. So we've got step 1, which is the slow step, and step 2, which is the fast step. So obviously that's the rate determining step. Now we've been given the rate equation for this, and you'd be given this. So this is rate equals K, CH33, and CBr. So this is what we've been told. So we need to identify which mechanism is the correct mechanism. Is it mechanism 1 or is it mechanism 2 from this information that we've been given here? So just a few things to note here, that the strong, in this example here, the strong CBr bond here in the haloalkane is broken, and this is a slow process because it needs a lot of energy to do that. And the second point here, this one's fast because there's a good chance of collision if there's enough OH minus ions floating around, hence why this is a fast step. So this is fast because we're reacting a positive and a negative together. This is going to have no problems reacting at all, but trying to break this CBr bond is going to be quite difficult, so that's a slow step there. That's why that's a slow one. So let's have a look. So the rate equation tells us that only CH33CBr can appear in our rate determining step because that's in the rate equation. So that's the only one that can appear there. Okay. So mechanism 1 shows us CH33CBr plus OH minus, and mechanism 2 shows us only CH33CBr. So that's what it only shows us. That is a closer match to that. Okay. So what we can deduce from this is that the suggested mechanism for this reaction is actually going to proceed via mechanism 2 because this matches exactly the ratio in our rate determining step. Okay, fairly straightforward. Okay, so there's not too much there to be concerned about. I know sometimes you look at these and think, God, these are really difficult, but they don't have to be. It's just trying to come up with a different way to look at it. Okay, and that's it. So that was quite a lot to cover in there. So that's everything you need to know for kinetics. Like I said, there's a full range of OCRB salters on Allery Chemistry. So there's for year 1 and year 2. There's also some generic whiteboard tutorial videos as well on there. They're all for free. All I ask is you hit the subscribe button. That'll be absolutely brilliant if you could do that. And also, if you would like a copy of these, I'll get any changes that I need to do. I'll obviously get them changed. But if you click on the link below, you'll be able to get a hold of them there. Great value for money and great for your revision. Okay, that's it. Bye-bye.